My name is Stefan Böcker. I'm from the Technische Universität in Dortmund, and today was invited to present Plan with EV, a European project, results as representative of Armin Gau, who is together with RWE and unfortunately was not able to present himself today. As a short remark, at the University of Dortmund, I'm working at the Communication Networks Institute, so my major subject field is not the energy part, but the communication sector. So I try my best to answer every follow-up question concerning energy parts, but if you have any question concerning communications within smart grids, do not hesitate to ask me as well. So, within the Plan with EV project, we mainly worked on the big challenge for network operations and especially network planning concerning a mass EV rollout and a high penetration of renewable energies. Starting with my first slide here, I have a comparison of grid capabilities on the right side linked to car capabilities, the charging capabilities of EVs. As you can see on the left side, there are relative high charging powers per single EV charging. For example, 43 kilowatts when, with AC charging and up to 200 kilowatts with DC charging. And on the right, you have your fixed traditional limits of the grid. As you can see easily here, if you want to guarantee a high charging power of simultaneously charging events at any time, you need to consider the connection directly at the medium voltage grid. To explain this a bit more detailed, I have here a small, simple topology of an energy grid. Starting with a feeder at the bottom of the slide, you can see a low voltage feeder with a limit of 200 kilowatts, connected several households with a mean power of 2 kilowatts. As you can assume, it's that in this case we have a huge amount of free capacity that could be used to install charging infrastructures. In these cases, if we assume that not all infrastructures are run simultaneously with a maximum power in parallel, the limit of 200 kilowatts wouldn't be reached. But assuming that at the transformer station 5 or 6 of these kind of feeders are installed, the transformer could get in trouble through the additional load of electric vehicles, for example. But this case is not the typical part, the typical example for the European grid. We also have in our Plan with EV project, for example, the Irish example, where we have transformer station with a definitely lower limit, for example here of 12 kilowatts, where just a single charging event could occur to problems within the transformer station. So the conclusion of this slide is that not the delivery of energy in the energy grid is a problem, but the challenge is the power that is connected in parallel to the grid. So one measure to handle these additional power is to invest in your conventional grid. So you could invest in grid reinforcements, which would directly lead to higher additional costs. Here is an example calculated with the worst case scenario, obviously, but leading to a number for a kilowatt price of 500 euros per kilowatt. So, assume an example, when there's no free margin in the grid, I have to invest 11,000 euros for an additional 22 kilowatt charger. Obviously, we all should avoid this, and it's cheaper to use these spare capacities than to invest in traditional grid reinforcements. That there are free capacities in the grid can you see here on this graph. The blue line is listing the load curve of traditional load households. As you can see, the grid is designed for the peak, usually around noon, and especially in the night times, I have enough capacity where I can switch active charging processes just to avoid additional power peaks to this traditional peak. Coming from the grid side to the EV side, we have analyzed 450,000 charging sessions in 2014. What you can see on the graph on the left side is the charging power divided by the maximum charging power of all simultaneously charging EVs. So what can you conclude of these analyses are two things. First off, you can see that in 300 hours per year, we've detected that our connected cars are charging with their maximum power, which means, okay, there are situations in the grid especially in big spots, big locations, huge car parks, where the load through EVs, charging EVs is that high that could cure some problems in the energy grid. But the second interesting thing is that the charging EVs in very most cases offer a high degree of flexibility which could be used in order to shift the charging process over the day. The charging behavior of the EVs directly is linked to their driving patterns, which means obviously when I'm at home, I usually charge overnight, or at work, I usually charge over daytime. In the public space, the charging behavior is kind of different and it's depending hardly on the facility where the charging location is installed. On motorways, there's a situation that they have only short charging durations, but therefore a very high charging power, which only offers a low amount of flexibility or even none. A very interesting thing is when we have analyzed these 450,000 charging session was that there's a correlation between charging power and charging location and the offered flexibility. In public, especially EVs that charge with a low charging power offer more flexibility than EVs that charge with a higher power. Here on the left side, you can see the average charging time divided by the connection time to the charging infrastructure. So in these cases, when the EV charges with 22 or 43 kilowatts, the EV customer plans their charging behavior in a good way, or even they wait while the car is charging, for example, when they have coffee or whatever, because the factor is nearby 1. If we go in the semi-public or in the private sector, we see another characteristic. Here, higher charging power offers more flexibility due to the reason that, for example, at work, usually working 8 hours, the connection time is fixed, and therefore a higher connection power, a higher charging power offers more flexibility, obviously. What we have now done with Employing with EV, with all this information that we've carried out before, is we have implemented holistic grid planning tool, which is able to plan new grids or the reinforcement of existing grids and the operation of grids. Therefore, we have collected several scenarios and use cases which are binded to several data, for example, weather data, temperature, solar, wind data, the mobility behavior out of several studies all over Europe, and obviously grid data itself and the area where the grid is installed. Thus enables us to generate the statistical behavior of EVs and the statistical behavior of DERs. And this is the input for our simulation tool itself, which is illustrated here on the right side of the bottom of the slide. This tool allows us to evaluate the behavior of the energy grid while having smart charging opportunities or not. So we can detect violations in the grid without having these smart charging options, and we can check what is the benefit of installing smart charging behavior in order to avoid these violations. And this is an iterative process, so you can detect several solutions or can simulate several solutions in order to find a nearby optimum solution. What we have also done in Employing with EV is we've tested all these measures that we have worked on in the field. We have 4 test beds, one in Germany, which is here illustrated. It's called the Smart Operator test bed. There we have our core unit, the Smart Operator, which is a kind of energy management system in order to implement the smart charging capabilities. And as a proof of concept, here you can see a screenshot of an app where the EV user within the testbed is able to enable an option which is called grid-friendly. Having this grid-friendly option enabled, the Smart Operator is allowed to play with the charging profile of the charging EV. And as you can see on the left side is the power profile of the testbed without the Smart Operator, and at the bottom left side of the slide is the power profile with the option of the Smart Operator. And as you can see here, it's possible to smooth the power profile by using these smart operator capabilities. Concluding my short presentation, and the main outcome of Plan Grid EV is that it's possible by using the smart charging operations to avoid traditional grid reinforcements. It's already today possible to implement these smart charging capabilities in the field. Currently, it's working with the IEC 161.8.15.1 protocol, but in future, all charging manufacturer and EV manufacturer should implement the 15.11.8 protocol as well, which offers several information, for example, the energy amount and the time duration, which is linked to a charging session. These both informations increase the capability of the smart operator because there's more information which you can calculate on. Here in German example, it's a paragraph of ENWG, which allows to reduce the grid fees for interruptible loads. This paragraph paves the way for example, the grid operator to implement the charge management and to give the customer some incentives. So as a main conclusion, the DSO should implement smart charging capabilities in the grid, and the field tests show that it worked. And for example, our planning tool is able to simulate the behavior of bigger grids, for example, all over Europe. Thank you very much.